I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on curved lenses, drawing ray diagrams using the focal length to use the lens mirror equation and magnification equation for double concave and double convex lenses. In this video, we're going to talk about curved lenses using ray diagrams, focal length to find image distance and object distance using the magnification and lens mirror equations. And we're going to talk about double convex and double concave lenses. So let's start with converging and diverging lenses. So here's a diamond shape that we're going to use to show how the light refracts as it goes through with straight edges. So we're going to draw a normal line at each surface, and we know that the one in the middle is just going to go straight through since it's traveling along the normal line. Each of the other two going from less dense to more dense, we know that the angle is going to get smaller in relationship to the normal, so we can draw the normal line at the other surface. We know now we're going from more dense into less dense, or a smaller index of refraction, so the angle gets larger. We can see that those rays of light intersect on the opposite side, which means this is called a converging lens. So if we look at another diagram where we have an object that is more hourglass shaped, and we again draw the normal lines to each surface, we can see the middle one still goes straight through, but when we end up drawing our rays for the other two, we know that again it gets closer to the normal. Then we draw a normal line on the other side, and again, going from more dense to less dense, it's going to go further away from the normal, and we can see those rays of light are not going to intersect. This is called a diverging lens. Now, if we look at these instead of straight lines, we look at them as curved, we have a double convex and double concave lens, double convex being a converging and double concave being a diverging lens. So let's start with the converging lens or double convex lens. So we have a lens, and the middle line again is going to be our principal axis. We can place the focal lengths and then twice the focal length, so the center of curvature. Now we also have a point right in the middle of the lens that we're going to call the center. And we're going to place an object outside the twice the focal length point. Now, when we draw a ray diagram, we know that the light's going to refract twice when it goes through the lens and comes back out. So we're going to draw this dashed line to just show once it reaches that dashed line, then we're going to see what happens after that. So we're only going to have it refract once because this is the way the ray diagram would work best. So we've got a line that goes parallel to the principal axis. Now the question is, which focal length are we going to use? Well, since we know this is a diverging lens, we know that those rays of light are going to intersect on the opposite side. So we need that blue ray of light to move downward towards our green ray of light. So we're going to go through this focal length, and that's always going to be true. Parallel rays of light will refract through the focal length on the opposite side. The ray of light that goes to the center goes straight through the center, so you can see they intersect. Now we could draw a third ray of light. Since we already used the focal length on the other side, we can draw a ray of light that goes to the focal length on the same side, and it refracts through parallel, and where those three rays of light intersect give us our image. So in this case, our image is a real image because the rays convert, it's inverted, and it's reduced in size. So we would need a screen in order to see this image, and you have to be on that same side as the image to be able to see it. As we move the object closer at twice the focal length, you can see it's going to be twice the focal length on the other side, real inverted and the same size. And move it in between the focal length, we end up with a real inverted and larger image. So that the image just gets larger and larger as we move closer and closer to the focal length. Now, what happens when we place the object inside the focal length? So we're going to draw those same two rays of light to start, where we have the ray of light hitting parallel to the principal axis, the one that goes to the center, and we can draw the ray of light going through the focal length on the far side, and the one that goes straight through. Now we can see that these rays of light are getting further apart, or diverging. They're not as close, they're not going to get closer together. If we draw that third ray of light that lines up with the focal length on the same side as the object, it's going to hit up near the top of the lens, and when it goes through the lens, it's going to refract off parallel. So you can see these three rays of light are not going to intersect on the opposite side, which means that we're going to have to extend the refracted rays back behind the lens to locate our image. So where the three rays of light intersect behind the lens, gives us our image. To do this, to find it, we know it's a virtual image, which means you can't reach out and touch it like you can a real image on the screen. We know that it's upright and we know that it's larger. Now, in order to see the image, you'd have to place the lens between you and the object to see the image. This would be much like a magnifying glass. So you use magnifying glass, you look through the magnifying glass to magnify whatever it is that you're looking at. So this double convex lens acts as a magnifying glass, makes images of objects to appear much larger than the object is. So let's look at a ray diagram for a diverging lens. So we place an object in front of a double concave, and again, we're going to draw our ray of light that goes straight through the center. That's always going to be the case. The question is, when we draw that ray of light that goes parallel to the principal axis, which focal length do we refract that ray of light through? Well, if it's a diverging lens, we know that the ray of light has to refract away from the ray that's already gone through. So we're going to use the focal length on the same side as the object to show how this ray of light is going to refract. So they are going to diverge. So they're not going to intersect on the opposite side. So since we've used the focal length on the same side, we can draw a ray of light that lines up to go through the focal length on the other side and refracts off parallel. So you can see these three rays of light are not going to intersect, they're diverging, which means that we're going to have to extend those rays of light backwards with our dashed lines, and locate our image is going to be again a virtual image because it's on the same side as the object, and it's upright, but this time it is a reduced size image because it's much smaller. Again, in order to see the image of this object, you'd have to be on the opposite side looking through the lens in order to see the virtual image. So you have to look through the lens, much like we did with the double convex inside the focal length. So the mirror lens equation, so we know that 1 over SO, the object distance, that value is always positive. If we add 1 over the image distance, that the image distance for the value is positive for real images, that's when it's on the opposite side of the lens from the object, and its value is negative for virtual images when the image forms on the same side as the lens. Equals 1 over the focal length. So the focal length, the important information for the focal length is that the value is positive for a converging lens, and the value is going to be negative for a diverging lens. So double convex is positive and double concave or diverging value is going to be negative. And then we have the magnification equation, the negative of the ratio of the image distance to the object distance equals the negative ratio of the image height to the object height, and that gives us our value for the magnification. Now, magnification, when it's less than 1, the image is smaller. When it's greater than 1, the image is larger. When the magnification equals 1, the object is the same size. When the value is negative, the image is inverted, and when the value is positive, the image is upright. Now, again, on your formula sheet, we're just looking at absolute values, so we're not going to have negatives. So you'd have to apply that in order to figure out if it's inverted or upright. So let's look at an example problem. So we have a 10 centimeter tall object placed 30 centimeters in front of a converging lens with a focal length of 20 centimeters. Question 1 is to draw a ray diagram to locate the image. So we can go ahead and draw our rays. We know that the rays are going to converge on the opposite side since it's a converging lens. So we can see that our image forms on outside of the twice the focal length point. And the next step is to find the height of the image and describe the image's characteristics. So to find the image height, we could use the magnification equation, but the problem with this is that we have two unknowns. We don't know the image distance or the image height. So what we're going to start with is we're going to use our lens mirror equation. So we know that 1 over SO plus 1 over SI equals 1 over the focal length. Well, we don't know the image distance, so we can rearrange that equation and solve for image distance. And we get 1 over F minus 1 over SO. Now we can do the inverse of both sides. And then we can substitute our values in for the focal length and the object distance and find that the image distance is 30 centimeters. We know that it's a positive value. That tells us that it's a real image, so we can start describing the characteristics of the image, knowing the positive value gives us a real image. We can bring back our magnification equation, and we're solving for image height, so we rearrange the equation, plug our values in, and we get the value for the image height to be 20 centimeters, which is larger. So we know that, number one, the image is real, it's inverted from our ray diagram, and it's larger based on the height that we calculated. Now, because the image height is inverted, we know that instead of doing the absolute value, when it's inverted, the image height value is going to be a negative value. So if we were asked to find the actual value, it would be negative. So this is an introduction to curved lenses, double concave and double convex. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X @Cabby Coaches.